Hello. Yeah, 310 makeup lecture. So I'm going to talk about how can I enable 4K and 8K quality in terms of the 3D video streaming. So we talked about the streaming mechanism. In the streaming mechanism is fetching down your playlist, and playlist is checking your files individually. Then collect the file and decipher or decoding it on the client side and able to see the video. Current network system can support up to 1080p, but over 4K and 8K it is not able to stream. Then how can I support it in the near future with the existing power? It is about the streaming in 3D video streaming. Let's talk about this. So various streaming platform and huge market size and increasing every year. So in terms of 2026, it is expected near $100 billion. So it is keep increasing as you can expect easily. The streaming platform will be the main size in the market. Also, they will be the main consumer of the traffic. Okay. So generation of media consuming, my father, maybe I am watch the TV with the antenna. Then I start to watching with the cable TV. Now start to watching computer in my notebook and downloading it. And now we are using a smartphone. Okay, what's next? Are we gonna streaming on the VR and AR devices? Probably, yeah. Then how can it be different in the current smartphone streaming to the VR AR? So migrating from the group audience to personal audience, meaning mobile devices we call the personal audience. The group audience is watching TV like. So we family watching the same TV, but I watch my YouTube. Okay. So it's the year of the 2018. So there is a grand cross. So personal device, a personal watch rather than a group watch is exceed the group watch. Okay, so in the near future it will be like more accelerated. Okay, the ratio of the watching personal devices more morely exaggerated. So which means I'm watching about 4 hours. Do you? So we used to watch 4 hours a day with the TV. Now we watch 3 hours a day. And personal devices, mobile device, we used to watch 2 hours. Now we are watching up to 4 hours. If you think about your Netflix, your YouTube, okay. So personal devices, AR users are increasing up to 110 million, okay. And the VR users are stay rough, but there's more, and we can see the trend. So I can see the VR and AR, the markets keep growing. So you know the Meta is betting on the XR. Okay. So if you think about the VR device has two main screen at your eye, right? So previously my watch, so I watch my smartphone at actual reading distance. I used to watch at the couch distance at the TV. So now we are at the eye distances, eyeglasses distance, whatever. So if I stream a 4K contents at 30 FPS, and if I watch the 1K by 1K per eye, and what I can see is actually only 240p, which is too low, okay? But my contents are 4K, but I'm watch only 240p. Why? Because my content is all around my headgear, which is 360 contents is 4K, which means the eyesight only I can see is 240. What if I want to see the 4K quality in my eye, which means I need to have 8K by 8K at the eye resolution, and contents wise I need a 24K at 120 FPS, which I need 2.35 gigabps network at the same time smaller than 10 millisecond latency, which does not exist in today's technology. Okay, so we are about at here second level, 30 millisecond and 100 Mbps at best. But 2.35, we never reached that point yet. Okay. So how can it solve this? How can it solve this? How can it overcome this limitation? The answer is machine learning. So we can improve automatically through the data. Okay. So we're gonna talk about bandwidth reduction in video streaming service with the VR saliency, visual saliency, and the visual behavior prediction. And the next one is a SR, super resolution. So salience-based video compression for 360 video streaming. Okay, this is published in MMSIS 2020. This is the top conference in the video streaming. So today's streaming service, we talked about in the classroom, we know what it is. The quality is ready on the server side, and you choose based on your network environment, okay? So based on that, I choose a medium, high, medium, based on your network environment. Okay, so we just saw this. Then there is a state of art. State of art is tile-based and geometric-based. Let's talk about the step-by-step. Tile-based is, I have 360 video contents, and I made a small tile into the contents. It's not just one file, I have independent tile contents. So if I'm looking at it here at the focal face, I'm watching the high quality. The rest of area is streamed in low quality. That's straightforward. Okay, that's very intuitive. Where I'm watching it is streamed in high quality. Where I'm not watching it is streamed in low quality. Even when I move around, I'm seeing still the low quality, but I'm seeing. Okay, the very basic is I'm watching only this, and rest of it is not prepared, which means if I turn around, then I see no video. Oh, what is going on? That's the moment I felt. The quality of perception is very low. Okay, so but this one, even I move, I see something. I see something in a low quality, but it's fine, right? So that if I can predict the user's behavior precisely, so predicting precisely doesn't make sense, but let's say I can predict it. Move, if I'm seeing the high quality, so I have to have precise video chunk, which means if I move within a video chunk, which is already downloaded to my side, then I have to experience a poor quality. Then turn around, that side become my foreground, face it. Then I stream the high quality from there. Okay, you got the point, okay? But if you think about who made a perfect prediction? Nobody, right? So perfect prediction is not possible theoretically. So, and the second approach is that this is Meta's, Facebook's approach. So rather than having equirectangular contents, they made it to the cube, then they made it to the pyramid, which means where I'm looking at is a high quality. On the side, gradually decrease the quality. At the point, I have the poorest quality, which means even when I move around, I see gradually degraded quality, which means a small movement I can accommodate, I can embrace it, but a radical movement I cannot, okay? So by doing this, by making to the pyramid, I can save up to 80%, which means a fifth of the data contents are needed to stream this quality, okay? So once again, perfect prediction is not possible. Therefore, even when I move, I see the poor quality. So our challenge is, can we compress the video content as close as a video encoding? Why? Because I can save huge contents. Okay? Can we embrace the unexpected user's movement? Which means even when I turn around, I want to see high quality. Or maybe I want to perceive as a high quality. How can I do this? So that's the answer for this paper. So let's look at this. Key design of the Salience 360 is salience's map built on the 360 video content. We know what the salience means, which means, let's say I just entered the room without knowledge. What do I see first? My brain, my human visual system see what is more distinctive than the others. If it is a classroom, I start to see the face of the student, okay? I don't see the texture of the room. I don't see that, not the normal people. So 99% human sees more distinctive point. So it is trained, and we start to call the salience map. Okay, what is more distinctive? Look at the example. So look at the example of this lions. Where do I watch? I prefer to watch the baby lion first. Start to see the face of the lions. A dog, face of the dog, and start to see structure. Maybe the only 1%, 0.1% of people may looking at the grass pattern. Okay, so we talk about 99%, the normal person. So how about this bird on the water? So I start to see, what is this? The unique pattern of the bird, are more observable than the others. We now understand what is a saliency. Okay, keep in that mind. So users' behavior, exploring behavior. So how the user's behavior? If I turn around slowly, that is fine. If I sort of radically move, then how can I embrace that? Embrace meaning how can I make the client perceive, oh, I'm still watching high quality. Okay. So Setlist 316 is from the cube map, this is original contents, I made it to the pyramid, and at the same time, from the cube map, I made it to the saliency patches. Okay, then I concatenated it to the stream. Now only the video is exactly pyramid with the couple of patches. So the client received a fraction of the contents and decoded to the cube map, and the patches are patched on top of it, which means where I'm looking at is high quality, turn around. So some points, whereas the salient than the others, that patches are patched with the high quality. So it takes some time to perceive, oh, it's a low quality, which means because I'm seeing first the 3 second, I'm only seeing the salient patches, salient points. So I'm seeing a high quality. I cannot deceive for 10 second, 20 second, but I can deceive 2 second, 3 second. Okay, which means perception-wise, that's a long enough time to make user feel I am watching a high quality. Okay, so how can I do the salience map? So visual map is more, so it is patch by patch, facet by facet. So I'm seeing, okay, that good contents, but I'm seeing the straight line, straight line, straight line. So a disconnected line is more distinctive than the others. So apply on the cube map doesn't work. So we made a bigger map. We rotate it as a one big picture. On top of one big picture, we run the salience map. So which is more logical, right? So then we apply the deep learning and a deviation degree. Then this is the resultant framework, salience patch with the face, and the rest of area is my pyramid, and these are my salience patches. So can I see? So these are the actual video streaming with the Setlist 360. On the left is a pyramid. On the right is a Setlist 360. Do you see this? Okay. Maybe I can. So this is streaming. On the left side is pyramid. On the right side is Setlist 360. On the VR device. Okay, can you see? Can you see the difference? Okay, go back to the slide. Sharing. My computer. So this is a post video. As you can see, turn around, and in the pyramid, I'm seeing poor quality of the human face. On the right side, this area is patched, so I'm still seeing the high quality of the video. And the letters are more distinctive than the others. Therefore, the letter area is patched with high quality. Okay, so we evaluate so Setlist 360's excellency over the pyramid. Okay, so how can it systematically evaluate the user's perception quality? So how can I make a metric for the perception quality? That's the perception quality we call the QOP, quality of perception. Then what are the benefits of 360, Setlist 360, and how can it embrace unexpected head movement? And is it actually work on the real users? That's what we evaluated. So we first made a metric. So FOB is a field of view. That's the common metric, common size of the eye, as you can see on the eye on the VL device. That's usually compared. But we believe the FOB is too wide to perceive as HOV, human HVS, human visual system. So we define an HOL, field of look. So where I can focus in this 8-degree value. So how can I define 8-degree or 90-degree? It is, we reference from the medical paper, medical science, what the humans perceive in the angle. So we reference these contents, and we decided as very conservative way at 8-degree. So medical paper says 2-degree is a degree that human can really focus on the pupil's degree. Okay, so conservatively for the systematically work, we use the 8-degree. So now we start to look at it, field of look. So where I can really feel the difference, really feel the high quality is 8-degree. So PSNR is a commonly recognizable metric. Its comparison is what's the PSNR is original video and now the decoded video. So we pixel by pixel, we check the differences. That's the PSNR. So let's look at the PSNR. So equirectangular is original contents with the 0 bandwidth saving and the, almost 100 PSNR, which is equal. So cube map, I save about 25% data, but I'm seeing almost 100% of the data contents, which is good. So pyramid, I can save up to 80%, but my quality PSNR in the FOV, I can only see the 30 dB. Okay, I lose a lot. So if I compare an FOB, Celis 360 use a little more of the data bandwidth. I'm using a little more of it, but I have a little improvement. Okay, but if we compare with FOL, field of look, I see the differences. Okay, so this chart is max 75%, 25% in average. Okay, so this 75%, 25% average value is commonly used in the statistics. So by using Celis 360, I'm seeing this. Let's look at the 75%. I consume a little more bandwidth, but I'm almost as equal as a cube map. Okay, and embracing head movement. That's the second challenge we are accepting, which means if I move around, okay, I'm seeing poor quality. So this from 0 to about 30 degree is a face-it video. Where I move it inside of it, I'm seeing the high quality. Okay, as I move around, I'm seeing the lower and lower quality. At the end, I'm seeing poor quality. Okay, if you remember the pyramid. So in the middle of it, so even I move around, because of my patches, I'm seeing the okay quality, okay quality, okay quality. Okay, so we tested with the actual users. There were 93 participants with the 10 different videos. MOS is mean opinion score. So after watching video, I see 5 is the best, 1 is the worst. Okay, so people responded as follows. So 5, CubeMap responded the best. Okay, the pyramid, okay, some of them were poor after watching some videos. Okay, but Celis 360 is very close to the CubeMap, but a little vote on the 3. Okay, and this is a Celis 360, and we're gonna move on to the SR, super resolution, the same problem in different mechanism. So DCSR is a data-centric super resolution and practical video quality enhancing using data-centric super resolution. Okay, so neural network-based video enhancing is original contents. If I run it bicubic meaning I make it to the smaller contents, I multiply, I make it amplify. So the filled gap, I'm using linear regression and fill in the in-between value. Okay, but if I'm using an SR, I'm seeing very close to the original. Okay, so I use the overfitting memorization instead of the generalization. So challenge of SR in practice. So bandwidth, burden, and delay. So since I have a delay, since I have a bandwidth limitation, if I can solve it in client size, client side, which means I downloaded this low quality, but if I can make it high quality, that's the magic start. Okay. So if I have to understand what is the data video streaming. In a video streaming, I have IPB frame. I frame is my reference point. P frame is in between references. I make many differences from the references. Okay, between P, that we call the B frame. So this is a data distribution. I frame takes most of the contents, and P frames this picks. Okay, difference to the iframe. So in between P frame, there's we call the B frame. This is a data distribution over the 2-second video. Okay. So we access to the hexacode because we have to test it on the hardware level. So we know where the starting point of the iframe, we know where the P frame, we know where the B frame starts. Okay. From there, we updated the hexacode. Then we run it on the real time. Now, without touching hexacode, it is almost impossible to run it in real time. So once I have an input video, I made it to the video segment, and from the video segment, I cluster into the groups. So why do I need to cluster into the group? Because similar groups can run on similar deep learning model. So I made many micro SR models. Then on the client side, video is downloaded and running a super resolution based on the model that I know, small model. Then I recover, then play in high quality. Okay, so videos, let's look at the workflow of server side. So input video is segmented into multiple contents, and feature is extracted, and I see which scene is this. Okay, then I made many micro SR models. Okay, so look at the features. So pipeline is, say I'm watching the interview or like a couch talk. Okay, the video segment can be different. It's something where I change something since camera movement is changed. I have to change my scene, but if it is consistent, people are just talking, I may have a longer video chunk. Okay, then I made it to the cluster. If I'm watching a friend's long contents video, a video is usually called scene 1, scene 2, scene 3, scene 4, right? If the scene 1 is very same environment with the scene 7, I can use the same model with the scene 1 and scene 7. Okay. Then I made a many SR model, super resolution model. Okay, so scene 1 is clustered into this same environment. Scene 2 and scene 3, we can cluster into the same group. Then from there, we trained the video model. Okay. Then I trained SR model 1, SR model 2, SR model K, which means from the low quality to the highest quality. Okay, I downloaded low quality, but I know if I know the relationship between low quality and high quality with the given environment, I can make a very tiny SR model. Okay, so now I have many SR models. Based on that model, the video is multiplied to the SR contents, and I'm able to see quality enhanced frame. Okay, so in time 0, I'm watching the segment, and I watch a download and cache. The scene is somehow changed. So level is 2. The new models are downloaded. So scene 2. Same model as previous one. I don't need to download it anymore. Scene 3, new model. Scene 2, downloaded new small model. I'm keep watching it. Up to 5, I don't need to download it anymore. Scene 6, once I change, I downloaded new model. So scene 7, if it repeated with the level model 1, I can still cache. I can use a still cached model. So we evaluated in the NVIDIA RTX. Also, we run in NVIDIA Volta, which is Justin Javier. Okay, so this is the performance of it. So HD video, full HD, 4K video with inference rate. Inference rate is smaller the better. Inference rate is smaller the better. But in terms of the FPS, as I have a small inference time, FPS is increased, frame per second. If I have a long inference time, I can only stream 1/2 frames per second. If I have very short inference time, which means I can play high FPS, which means 60 or 70. So in this graph, so the higher the better. So number of inference per segment is 5, which means the NAS, the competitor, needs only can serve 1/2 frame per second, but and the NeMo is our competitor, is an increased version of the NAS. It can serve up to 20 FPS. So for the user side, if I don't want to feel jittering, so it should be more than 30 FPS. So DCSR is the first model which exceed 30 FPS. So full HD. So my target is 4K, 4K and 8K, right? So to make it happen, to make it to the full HD from very small content, which is 240 and 480, then I can see to support, able to support is only DCSR. Okay, so from streaming to the 4K, even I can do the 4K streaming. Okay, only the DCSR can support. Okay, so enhancing rate to the 4K resolution, if I can see with the laptop and desktop, previous result was on the smartphone environment, a mobile device environment. As I can have the DCSR is only device which can support live stream. Okay, so NAS, I need to fetch. NAS is basically per frame resolution. So I have to run my deep learning every time. So I have to run it 30 times per second. But DCSR only apply on the iframes. Therefore, I can work, but rest of it work, and rest of it work, and rest of it. So I'm using very small power consumption. Okay. So evaluation on the PSNR, SSIM is the same metric we discussed in it earlier. So PSNR higher the better. So DCSR stays high, NAS better, but NAS and NeMo is better. But if you compare with the previous metric, it is almost same. So in practically, to run the DCSR, number of network users is SSIM, the higher the better. So DCSR stays as the same as NeMo, and number of normal network users is smaller the better. So I'm using smaller network and able to consume high quality with using super resolution. So recap. So we just covered how can he stream the 4K and 8K quality in the mobile devices when the incoming incoming VR and AR era. Okay.